In English. Yeah. I'm going to stay this side in order to pass the slides. Okay. Well, this talk is aimed to present recent work and ongoing work about Gribov and trying to make some relation and correlation with phase transitions. And well, let's start. Here's the outline of the presentation. I'm going to start with a very basic introduction about quantum theory, and then about gauge symmetry and fixing gauge. And then I'm going to start with the Gribov and Bibit. I'm going to give a very simple and the original Gribov proposal to solve at least part of the problem of the Gribov of the problem of gauge fixing, in specifically the Landau gauge. And then I'm going to start to talk about the phase transition. Okay, the third section here is related with Gribov, just an interpretation of the two-point function of the gauge field But then in the last section, I'm going to talk properly about the phase transition, and I would like to make it very clear about the difference between the thermodynamical phase transition, a finite temperature study, and a topological phase transition that which is part of ongoing work. Okay, so let's start with the Yang-Mills action. Well, here we have the Lagrangian of a scalar field, and this Lagrangian specifically is not invariant under gauge transformation. A gauge transformation for a scalar field can be written like this, where this u of x is an element of the SUN, of the group of transformation. And in order to recover, in order to have the gauge invariance, we just add another field we call the gauge field, an interaction with the scalar field in this case, and the normal derivative becomes a covariant derivative taking into account this new field, the gauge field, the vector field. And the gauge transformation of this new field is given by this transformation rule here, and also alternatively by this this last expression. They are equivalent. Okay, and
yeah, this is the first one is the infinitesimal one.
Yeah, sorry. Yeah, indeed, they're not equivalent. The first one is the infinitesimal one, mm-hmm. And the last one and the last expression is the exact one. Okay. Okay, and now the action for the scalar field is written like this, and where V is the potential. Okay, and since we introduced the new field, the vector gauge field, we need to quantize this field, and for that we introduce the Yang-Mills action, where F is just the commutation of the covariant the commutator of the covariant derivative. Okay, and finally the action with the scalar field and the vector gauge field and gauge invariant action reads like this last expression here. Okay, so okay, finally we have the gauge invariance, what it means actually, and why is that good, and perhaps why it's not, I don't know. So, well, gauge invariance is good in many sense that I'm going to show in the next slide. But we say that A is gauge equivalent to an A prime if they're linked by a gauge transformation. And here again I put the infinitesimal gauge transformation. And we say that they belong to the same orbit. Okay. And this I showed you this action is gauge equivalent and takes into account the gauge field. In order to quantize, the path integral takes into account every possible configuration of the gauge field. So we are considering even the gauge equivalent configurations. But okay, is there a problem? Well, physically it is a problem because it's a kind of ambiguity. Why it is an ambiguity? Because with gauge independence, we can speak properly about physical content of the theory, in the sense that a physical quantity must be gauge independent, in the sense that if we perform a gauge transformation, the physical quantity shouldn't depend on this transformation. Okay, so that is, if A and A prime they are gauge equivalent, they are accounting, they are linked or accounting for the same physics. It means that in principle, in order to not be, in order for the path integral not be have ambiguity, we should pick up only one configuration, at most only one configuration at each orbit. Each orbit, it means that we are performing gauge transformation. Okay, a gauge transformation on a field will define an orbit, and then we should pick up only one configuration. And then a gauge condition is just a curve that in principle should cross at most once each orbit. Okay? And well, now we have to impose this condition, the gauge condition, in the path integral. And this is done by traditionally by the Gribov procedure, which is more or less introducing a very smart number 1 in the path integral. Okay? What it means, this number 1. Well, here we have the Jacobian, because we perform an infinitesimal gauge transformation in the gauge field. Okay, so if you were transforming the integrated quantity, you should consider the Jacobian. And by definition, it should be quite clear that by definition this is the moduli of the determinant. And here we have the delta, which exactly this f, this fancy f, should be this f here, the curve that crosses each orbit. So in order, this delta is forcing the path integral to be integrated over the curve f. Okay. So here we have the delta function of f of the curve after a Fourier transformation, and for this we introduce an auxiliary field, the Nakanishi-Lautrup field, if I'm not mistaken by the name. And okay, we should treat the functional determinant, and we treat like this. We introduce two new fields. They're Grassmannian fields, and we call them ghost and anti-ghost, for reasons that they don't belong to the physical spectrum of the theory. But okay, it should be quite clear that in order to introduce ghost and anti-ghost in this way, we are talking about the determinant, the functional determinant of M. This M is exactly this functional derivative here, and this is the Gribov operator. I don't quite remember, but I believe I'm going to write this explicitly for the case of Landau gauge. And it should be quite clear that here we are not considering the moduli, okay? So in principle we consider the possibility that the determinant be 0 or even negative, okay? And let's see what happens in the Landau gauge. That's the condition of the Landau gauge which defines the curve, okay? And here we have the Jacobian, the functional determinant, and that M, fancy M, now is the Gribov operator written explicitly like this. The Landau gauge is a very specific, and in some sense it's a nice gauge, okay? so to say, because the Faddeev-Popov operator is an Hermitian operator. So we will not see, but at the end we need to look at the eigenvalues of the Faddeev-Popov operator and analyze which one is bigger than the other. Of course, this is only possible if the operator is Hermitian, so the eigenvalues are reals. Okay, so let's work in the Landau gauge, and this is the expression of the Faddeev-Popov operator in the Landau gauge. And here again we have the partition function. I put a star just to make it clear in red color, just to make it clear that the Faddeev-Popov partition function star is not exactly the same as the previous Faddeev-Popov partition function, exactly because here we have the modular of the functional determinant, and here in the star partition function we have the ghost and anti-ghost. And as I mentioned in the previous slide, in order to introduce the Grassmannian fields, we are ignoring the fact that it can be negative. Okay, so they are not exactly the same, and this is basically the source of the Gribov problem. Okay, in order to construct the partition function, we made two assumptions. The first assumption is that the curve crosses once each curve, and the second assumption is that the determinant is always positive. We hope that this is true. However, both of them fail. Okay, and in some sense, they are the failure of one is linked to the other one. Okay, well, here we have the f, the curve. This is f, and this other curves here, L prime, and 2 prime. They are the orbits. Okay, so it's possible that the curve crosses only once, twice, or even doesn't touch the gauge condition. Okay, so we hope that only the first case happens. However, it's not true, and I'm going to point more or less that this is not true. So it crosses more than once. It would also be possible that it doesn't cross. However, it doesn't happen. And here we have what happens. So let's consider that A and A prime, they are gauge equivalent, so they're linked by a gauge transformation. And now let's impose the gauge condition and say that the derivative of A and A prime, they're 0. So at the end, the equation we have is exactly like this. Okay, this expression here is not exactly this one, because this one is the exact gauge transformation. However, this last one, I took the infinitesimal gauge transformation. Okay, but so and this is the expression we have when we impose both conditions. And now you see that it's possible to exist 0 modes of the Faddeev-Popov operator. Okay, infinitesimal 0 modes, because we are considering infinitesimal gauge transformation, and this is one of the important issues of Gribov problem, because we are only considering infinitesimal copies, not the most general ones. So, okay, the first question is, okay, you're working in the Landau gauge, but what happens in other gauges? Well, in a work of 1978, Singer, I don't know if that's how to pronounce his name, but anyway, a very important and in some sense well-known paper says that every covariant gauge is plagued by Gribov copies. Okay, it's good to know, but another problem is to analyze the copies, because it's easier when the Faddeev-Popov operator is Hermitian, but in linear covariant gauge, for instance, the Faddeev-Popov operator is not Hermitian, so it complicates a lot. Okay, so at least the Gribov problem is apparently only a problem of the Landau gauge. Every covariant gauge is supposed to be plagued by these problems. Okay, so Gribov proposal to solve more or less the problem, more or less in a first sense that we are considering infinitesimal gauge transformation, in another sense that I didn't put in on the slides, but we already know, it's already well known that Gribov restriction, I'm going to say what is this restriction, it doesn't take into account every possible copies that they are on this region, in this region. Okay, so in many sense this is a first trial. We can argue that this is a first good trial, but it is a first trial. Okay, and what is the trial? So we analyze the Gauss two-point function, and we look, because the Gauss two-point function is related with the inverse of the Faddeev-Popov operator. Okay, so we look for positive and negative eigenvalues of the Faddeev-Popov operator. And here we have the regions. This is the domain of gauge field configuration. In the first region, called the first Gribov region, we have positive eigenvalues, and then it goes until get closer to the border, and on the border you have the first zero modes, and then it's negative eigenvalues and so on. And Gribov proposal is to consider only positive definite eigenvalues, the region of positive definite eigenvalues of the Faddeev-Popov operator. Okay, this is this omega, the first Gribov region. Every possible gauge configuration, satisfying the Landau gauge, and satisfying the condition that the Faddeev-Popov operator is positive definite. Okay. In this way, in principle, we should eliminate the copies, but we know that they're not eliminated. But okay, this is the Gauss two-point function, and sigma is the form factor. The condition to restrict in the first Gribov region, it is translated to the Gauss two-point function by this condition here, where sigma is smaller or at most 1. Okay. Well, it is computed at zero momenta because we know that. Let me remind. We know that the bigger the momenta is smaller the eigenvalue. So since we're looking at the smaller, the highest eigenvalue, possible eigenvalue. Sorry, let me think again. Yeah, we are looking at the smallest possible eigenvalue of the Faddeev-Popov operator, and this is got at zero momenta. And then we have this condition, which is called the no-pole condition. And okay, compute up to first loop order in perturbation theory. Okay, it is important to mention. Okay, this is parameter, the dimension, the volume of color space of the group, gauge group. G is the coupling constant, and it's very important to see that this form factor of the Gauss two-point function is non-local. It depends on the inverse of the momentum, the squared momentum. Okay. This is important to understand the theory in the sense that it's non-perturbative. It captures non-perturbative effects of the theory. Okay. And then the partition function that satisfies the no-pole condition, which is the Gribov partition function, like this. Okay, this we introduced the Gauss and the Gauss, and now we have the theta function, the step function, which is just to be restricted to the first Gribov region. Okay, it is 0 outside and 1 inside. So it is 1 when it's non-zero when the no-pole condition is satisfied, and otherwise it is 0. at the end we have.
Sorry, why again does it have to be at zero momentum? Because you are going to some number of configurations, right? So
Yeah. Wait, let me. I'm trying to remember why it has to be in zero momentum.
Large momentum. The inverse propagator grows like p squared. So and zero momentum is zero. So you can expect that the worst case is zero.
Yeah.
it's because it's related to the pole.
Yeah.
Yeah, it's related to the pole of the ghost function. Yeah.
So you can imagine that the pole appear at first at zero momentum. But this is again an educated guess. Beyond and one loop is clear, but beyond.
Yeah, at one loop it's clear. But here, for instance, the only possible pole is when k squared equals 0, and the worst case is when momenta is 0. So we consider the worst case when momenta is at 0 momenta. So we have only one possible pole for the ghost-2-point function. Okay. But okay, well, at the end, we need to put the step function in the actual level, and in order to do this, we introduce the a beta parameter, which is the Gribov parameter, okay, which is not free. It will be fixed by the self-consistence condition, which we call the gap equation. As usually we do for self-consistence condition, and this is the Gribov action, where beta, okay, is not a free parameter. Well, making a dimensional analysis, we see that beta is proportional to the volume of the space, and then we consider the infinite space, the thermodynamic limit, and in this limit, this logarithm term here can be disconsidered, and then this step function becomes a theta function. It can be seen here more or less because we have here the log, okay, exponential of logarithm of beta. But if in the thermodynamic limit we don't have this beta, and all we have is just beta times an expression which is a delta function. So in the thermodynamic limit, the step function becomes a delta, and then this is the self-consistence condition. The no pole condition can be read of as this gap equation. This is more or less the no pole, satisfying the no pole condition. Okay. So we have the action, we satisfy the no pole condition, get back to with the beta star. The beta star is is the value of beta that satisfies the no pole the gap equation, and put it back in the action. Okay, and now let's start to compute the 2-point function of the gauge field. We have at quadratic level, we have this operator here. Yeah. In order to compute this properly, we had in principle we had a no-local expression I mentioned previously. We have a no-local expression because we have a squared AA over momentum squared. So we need to localize the action before getting this expression here. But okay. In any case, we have this operator. The Landau limit is recovered when we take C, which is the gauge fixing parameter. We integrate out, and what I have is this expression here. This is the vacuum energy density, and the gap equation can be the gap equation that is the derivative of the vacuum energy equal to 0, and then this is the gap equation. This is very interesting because the gap equation is exploding, is divergent. Okay, so we have to renormalize. We have to choose a renormalization procedure. And for instance, and here what you have at the end is the Gribov parameter. Sorry, just mentioned before, the Gribov parameter, I was saying it was beta, but there is a small relation here relating to gamma, just to redefine the parameters, okay? Nothing more. So the Gribov parameter is proportional to the renormalization scale and proportional to exponential of -1/g squared. So in the infrared limit, where the coupling constant is big, the Gribov parameter is really small, and then we recover the. Sorry, I'm saying something really exactly the opposite in the ultraviolet, and then we recover the perturbative, well-known mechanism for the gauge field. Okay, so again, in the ultraviolet limit, the Gribov parameter is quite small, and then we recover what is well known in the perturbative, exactly because of this behavior of the inverse of g squared, exponential of the inverse of this g squared, minus, of course. So it decreases. Okay. Well, and what about the Bloom propagator, the two-point function? It is written like, it's just to compute the inverse of the operator I mentioned 2 or 3 slides backwards. And taking the Landau limit, we have exactly a transversal propagator with this form here, which can be rewritten in this way in order to make explicit the complex conjugate poles. Okay. And now we're gonna this slide here, I called it from physical to non-physical excitation, exactly because in the ultraviolet, as I mentioned in the previous slide, the Gribov parameter is really small, almost zero, and then you recover the perturbative results of gauge field, and it's physical. However, when the Gribov parameter, when the Gribov problem has to be taken into account, you have complex conjugate poles, and this is not physical anymore. And there's also another possibility when you have negative residues. You also lose the physical interpretation or the possibility to get back to Minkowski, because all the work is being done in Euclidean. So you're not able anymore to get back to Minkowski and to relate these two-point function to a physical particle. Okay. You have any?
Yeah, no. B is, it depends on K is B.
Yeah, sorry. Yeah, sorry. Yeah, indeed. Just too lazy.
There is the projector you put with K and the.
Yeah, even worse. Yeah, in the slides before I was relating, talking about K was the momentum, and here even worse I wrote K, but no, this should be P. Okay, the transversal operator is with respect to the carried momenta by the two-point function. Okay,
so this is for a theory like SUN.
Yeah, for non-abelian gauge transformation. Yeah.
So you have this tachyon. No, not tachyon.
This is not actually a tachyon because
it's worse.
It's worse than a tachyon. Yeah, it's worse. Yeah. Because the pole itself is complex conjugate. It's complex conjugate, not the mass, but the pole. The squared mass, more or less to say. So, yeah. And okay, and since before in the ultraviolet you had a physical interpretation of the two-point function, and now you do not have anymore a physical possible interpretation of this quantity here, it can be a point, a sign of confinement. But of course, this is very tricky, very complicated, and very, I don't know, dangerous to talk about confinement, looking at a gauge-dependent quantity. A two-point function, it obviously depends on the gauge field, of course, not quartz, but the gauge field depends on the gauge field or the choice of the gauge field. So how can we talk about physical quantity like confinement? It's physical, looking at gauge-dependent quantity. Okay, so of course it can be a confinement, a sign of confinement, looking at a gauge-dependent quantity. So, but okay, I already mentioned this slide. That it's not possible to get back to the Minkowski according to the conditions by Osterwalder-Schrader. It's not possible to get to the Minkowski spacetime and then give a physical interpretation. Even more, the Kähler-Lehmann spectral representation is not always positive for this propagator. So it's not also possible to attach a physical interpretation for something that has not an always positive Kähler-Lehmann spectral representation. Okay. So here is the problems more or less of the Gribov propagator, Gribov blue propagator. It's not always positive, the spectral representation. It's not possible to get back to Minkowski, and therefore the group propagator does not belong to the spectrum of physical particles, asymptotic physical particles. Okay, so I read more or less, I mentioned that slide. So let's start to talk about finite temperature.
But you present that like a problem, and indeed it is a problem, but this is a realistic problem in the sense that the true propagator of gluons measured on the lattice is that way.
Yeah. It's not a problem itself. It is like it is. Okay, it is like it is. You have to accept and try to interpret this. Okay, even if you work with Gribov problem, or even if you work with a massive gluon propagator.
Or you measure the lattice.
Yeah, what you measure in the lattice is exactly something that behaves like this. Okay, so apparently nature is like this way. Apparently because, okay, lattice, sometimes we directly relate lattice with reality, but not actually. This is a computer. But so, finite temperature, what we do, this is more or less already old paper. It's about 2 years more or less paper. 2 years ago paper, and what we do is to check phase transition looking at the Polyakov loop. Okay, the Polyakov loop is defined mathematically as this quantity here, and it represents the potential between two static quarks, quark and anti-quark. Okay. And we choose the Polyakov gauge, which is we fix we choose the Cartan subalgebra in the sense that only the third component in the color space is non-zero. Okay, not the third. Yes, the third, specifically the third. And with this choice here, the Polyakov loop is quite simplified and can be written like in this way here. Nico is very well an expert on.
But so two things. The interpretation is not really the potential between. Is the logarithm of that is the free energy of a single quark in a thermal path.
Yeah.
It's not
the static.
In order to have the potential, you need to Wilson.
You have the Wilson loop. Sorry.
This is just
right. You're completely right.
And here. A0 must be taken into with care, because this is in the background gauge. This expression.
Yes. It has to be taken in the back. Indeed, for sure. This Polyakov gauge, it has to be applied in the. We consider a background gauge, okay, a fixed classic background gauge, and then we fix exactly because at the end. As I'm working with Gribov, I need a quantum gauge field, which I will apply the Landau gauge. So this Polyakov gauge is being applied in the classic background gauge, okay, that we consider, which will play the role of the Polyakov loop. And indeed, the potential between two quarks is not a Polyakov, but the Wilson loop. And the difference is in the, well, mathematically, just looking here, just here the exponential is slightly different.
What was beta there?
The inverse of temperature.
Uh-huh.
No,
Yeah.
yeah, the inverse of temperature, yeah. Exactly. Okay. Yeah, here beta is the inverse of temperature, and before I was saying that it was the Gribov parameter. So
So,
okay.
here is like a, yeah, the Wilson loop around.
Sí.
Yeah,
It's not the same bit.
Oh,
this is not the same beat as before. Yes. Sorry, but. But okay, what we do, the first thing to be done is to fix the Gribov parameter, and here I'm using lambda and not gamma as before, and again we're going to update the Gribov parameter. Now it's lambda, and this is the gap equation, okay, which has to be applied in order to the theory make sense. And we are going to look for phase transition, looking at the second derivative of the vacuum energy density with respect to the, we're going to call this R as the Polyakov parameter, okay, with respect to the second derivative of the Polyakov parameter. And then we just suppose, let's suppose, this is not essentially true, but let's suppose that the Polyakov parameter minimize the vacuum energy. Okay, let's look for a configuration of the Polyakov parameter that minimize the vacuum energy. This is just supposition, but before let's do the job just taking the second derivative and look for the phase transition. And what we have, looking at the second derivative, is a second order phase transition. Okay, but here please pay attention that all the values here are in units of lambda 0. Lambda 0 is the zero temperature Gribov parameter, but actually this is the Gribov because there is a refined version of Gribov that fit the lattice. Okay, I'm not talking about this in this presentation, but Gribov itself, it doesn't fit the lattice in the deep infrared. However, there is a refined version of Gribov that does fit the lattice, and therefore for Gribov, this work, we don't know the value of the Gribov parameter. So every computation here is in units of the Gribov parameter. Okay, we have more or less an estimation for the refined Gribov-Zwanziger construction, which is the one that fit the lattice. And this gives us a critical temperature of dot 25 GV. Okay, which is not that far from what is found on lattice, which is dot 295 GVs. Okay, and we are more or less happy. It's not that far because this is just a first trial for RGZ. RGZ is much more complicated than Gribov construction. Okay. But okay, this is the phase, a second order phase transition. It is very important to stress this, that our theory...
this is SU2. SU2.
SU2, yes, SU2. For, I believe that for SU3, it is first order.
Yeah.
Yeah.
So pure Young-Mill theory and SU2.
Yes, pure Young-Mill theory, no scalar field, no fermionic field, and SU2. Okay. It's important to mention that I didn't mention, which is a very important feature of any massive gauge field. Okay, that the PRCT symmetry is broken. Okay, we have the gauge symmetry. When we fix the gauge, obviously the gauge symmetry is broken. However, there is still a sort of gauge symmetry which we call PRCT symmetry. I didn't mention here. It has It's a failure of mine. But when we consider any massive parameter for the gauge for the gauge field, also the Beer-City symmetry is broken. Okay, so we don't have anymore the gauge symmetry, not even the Beer-City symmetry. It's important for the sense of my presentation, which is talking about symmetry, phase transformation, phase transition, and in a few slides I'm going to talk of the topological phase transition.
Oh, you don't have the gauge symmetry because you fixed it, right?
Yes, when you fix the gauge, you lose gauge symmetry, but Beer-City can be seen as a sort of gauge symmetry, a sort of gauge transformation. Okay, but even Beer-City is broken. But okay, reminding that I have the gap equation, and we are supposing, okay, that the Polyakov loop parameter minimizes the vacuum energy. Why do we do this? Because with the first equation we have lambda, the Gribov parameter, in terms of temperature and R. With the second equation we have the opposite. We have the Polyakov loop parameter in terms of temperature and lambda. Okay, and then we can see how they behave with respect to the temperature. Again, in units of the Gribov parameter. And what is most interesting here is that when here the phase transition occurs.
So you are presenting here, what are you representing here?
Okay, yeah. What I'm representing here is just how.
What is represented is R of T.
Yes, R of T. The dot line is the behavior of R, which is the Polyakov loop parameter as a function of temperature. Okay, and the continuous line is the Gribov parameter as a function of temperature.
So in the first region, the numbers there is pi.
Yes, pi.
Okay.
Yeah, it's pi. And the phase transition occurs more or less here. And I gave this number in the previous slide. Okay, but okay. Yes, this number is pi. Okay, for R. And here it is one is like above one, and then it has a very clear, sharp change of behavior. Okay, and this is very interesting because the Gribov parameter follows the phase transition. Okay, the actual phase other parameter phase transition is R, the Polyakov loop. Lambda, the Gribov parameter, is not another parameter phase transition. But in a first trial, in a first study, we can see that the Gribov parameter follows the phase transition pointed by the true order parameter, which is R. Okay. So now let's point to the problems. Well, the main, and Nico agrees with me, is with the pressure. When we compute pressure, okay, we always have this negative regime, a regime with negative pressure, okay, and we don't know how to more or less how to solve this, how to treat this negative pressure.
And after that you have your oscillation.
And also you have, yeah, this oscillation here, yeah.
And then you arrive to a positive pressure in the extreme infrared.
Yes. It is clearly for us. It's clearly positive in the deep infrared.
Okay.
And when we consider RGZ again, the refined Gribov prescription, which is quite complicated, and we have just a first trial. We know that this is not the right trial, okay? But we got a smaller negative region, but we still have a negative pressure.
It doesn't solve the problem.
It doesn't solve the problem, and we know that it's for sure it shouldn't have, because when you consider just a massive model,
The same appears. But our curve is not the same. We have the same problem, but the curve is different.
Yeah, but okay, we are more or less.
Because we have our pressure in the infrared is negative, but it's extremely small. You don't see that in the curve.
And this disappears in deep infrared, the
In the
negative.
infrared goes, okay, in the deep infrared, what? The curve is different. I don't.
I don't remember the cover you showed the paper. I've seen many times, but this paper,
Okay.
I don't remember exactly.
Okay. But you see, I still do not understand, because your curve should go to zero at zero temperature, because it's the difference between the thermal, the pressure at finite temperature and
Yeah, okay, I agree. I don't remember what we got for, with the RGZ, and this can be the case with RGZ because in the infrared, in the deep infrared, we know that Gribov drastically doesn't agree with lattice. Okay, for sure Gribov is not a good model for deep infrared. I don't remember the plot for RGZ, but for sure Gribov is not a good one. I don't remember. I can even see later and then show you.
okay.
But okay, let's now talk about topological phase transition, how it works, and then talk about our what we are thinking about our proposal for phase transition in topological models. Momentum space topology is a framework completely different from, let's say, it is another way to classify quantum field theory, to classify the ground state of quantum of relativistic quantum models. Okay, it's another way to classify, and this is more or less equivalent to topological materials, as it is already known, but perhaps not well known. I don't know how much it is well known that the standard model above the electroweak scale, it is equivalent, it's topological equivalent to superfluid helium-3 in the phase A, or even semi-material topological semi-metals. Okay, they belong to the same universality class, topological universality class. Okay, at the end, momentum space topology, it's a framework to classify the theory topologically. Okay, and one of the universality class is the Fermi point, and the standard model above the electroweak scale. In this regime, we have chiral fermions, and this is topologically equivalent to semi-metals, for instance, or superfluid of this type here. I'm far from being an expert on superfluid and topological materials. Okay, but okay. In any case, this is another way to classify, and the classification works with this with topological invariants. We have there are topological invariants that, according to the topological charge, you can classify the theory. Okay, but what's main important, what's really nice is not the classification itself, but phase transition. The phase transition, it happens when you have the same topological invariant, and I'm going to explain what is the same actually, and the number changes. Okay, you have an integer number, and in another regime of the theory, you have another number for the same topological invariant, and then you can talk about topological phase transition, which is not the same as thermodynamical phase transition, first order, second order, and so on. But okay, let's see more or less what this quantity here. This quantity we call a topological invariant, but this is not always topological invariant. It has to satisfy two conditions. And let's go. Let's by part. First, the integral is over the hypersurface defined by the time component of the momentum equal to 0, squared is equal to 0. This red K here, it takes into account the symmetry of the system. Okay, the system can be the ground state of a quantum field theory. The system can be a topological material. Okay, but this K will take into account the symmetry of the system. G. It's written wrongly. You see that G, dg minus 1, G, dg minus 1, it's missing one G here, okay? It's G, dg minus 1, cross product G, dg minus 1. So, and G is the 2-point Green function, okay? Yes, this N is just a normalization factor which depends on the space symmetry we are considering. The space, the 2-point Green function exists. For instance, for fermions, you have the fermionic indices, okay, and then you take the trace. You have the trace over the space of fermionic indices, and you should normalize. And this is the normalization factor. Okay, we should apply. Otherwise, obviously, this is not will be an integer. But when you put the right randomization factor, you have an integer. Okay? And of course, this is not any normalization factor. As I mentioned, this is the trace over the space the 2-point function exists. So, in order to be a topological invariant, it should satisfy two conditions. The first one is this quantity here, the matrix representing the symmetry of the system should commute with the Gribov, with the Green point function, and the Green point function should satisfy the boundary condition. The Green point function. I'm talking. Yeah, the
2-point function.
The Green 2-point function. Yeah. Okay. It must satisfy the boundary condition. Okay. On this hypersurface. Okay, satisfying both conditions, the integral showed is a topological invariant. Okay, so let's see what happens. An example. Here, please. I'm not really an expert. All this result mainly. This result here is a result from Volovic in this work here, and for Weyl fermions, massless Weyl fermions, fermions, it's possible if we put k equal 1, the topological invariant is 0, which means that the symmetry of the system is not topologically protected, in the sense that if you turn on interactions of fermions with any other thing, it can become massive. Okay. For instance, the chiral symmetry is not protected, but it's possible to find a topological invariant whose number is not 0, okay, whose charge is not 0, the topological charge is not 0. In this case, the symmetry of the system is topologically protected by the topological charge. Okay. Yeah. And this is the case equivalent to semi-metal state. Okay, they call this the semi-metal state. Okay, and well, for massive fermions we have this expression, and for massive fermions we must consider the charge time symmetry transformation, which is given by gamma 5, gamma 0 Dirac matrices. The Green 2-point function for massive fermions is given like this. Z is the renormalization factor. Okay, in M of p squared. This shouldn't be capital P. Okay, it's a small p, and this is the dynamical mass. And well, if we consider a toy model of this dynamical mass working as a constant mass m0 plus a dynamical, a momentum-dependent mass. Okay, this is really not the case because lattice point for a constant over p squared, something like this, over p squared, not multiplied by p squared. Okay, so this is a work 2010, but he considered this toy model. Okay. Well, then he computes, and let's see what he found. What he finds. The situation is to consider many possible values for m2 and m0 and see what happens. Okay. Another thing. Let me get back here. This topological invariant is completely different from the topological invariant of massless fermions, which means that we cannot compare both things. If we find different numbers, you cannot say nothing because we are comparing different topological invariants. This one is related with charge time symmetry, and the other one is related with rotations in the left-handed value fermions. Okay, so topological, they are completely different topological invariants, so you cannot compare. What you can compare is for different possible values of m0 and m2. And okay, these are the situations. For m2, the dynamical part positive, the topological invariant is 0 if we have positive constant mass, and -2 if the constant mass is negative. Okay, so what it means? We have the same symmetry with this charge time transformation, gamma 0, gamma 5, and we have the same topological invariant. However, we have two different values, 1, 0 and -2. And here we can talk about topological phase transition, because we are comparing two different situations of the same topological invariant and two different values. And in another region, when the dynamical mass is negative, we have +2, +2 if the constant mass is positive, and 0, I put minus. Arriving from left. Okay, you have 0 if you have negative constant mass. Okay, in this case we have topological phase transition, and we cannot compare with the massless, with the chiral fermion situation, because they are different topological invariant. Okay, it is at least more or less clear.
I don't have clear what's the role of Gribov problem with this.
Yeah. Indeed. I believe that's the next slide. Yeah. Let's talk about what happens with the gauge field. Okay, and this is what we are proposing to be new. Okay, what we are proposing to be new is it should be more or less clear. We hope to connect the Gribov parameter, not the Gribov parameter, I'm not sure, but okay, the gauge field propagator with topological phase transition. We cannot do this with thermodynamic phase transition. In the thermodynamic, we looked at the Polyakov loop. We were not looking actually at the Gribov parameter, but here we hope we can look at the gauge two-point function, gauge field propagator. Okay, but the first question is, okay, every work is done for fermions. The question is, should the gauge field propagator play some role in the topological invariant? Because in the definition of topological invariant, you just work with green two-point function. We can define we have a green two-point function for the gauge field. So what happens if we just plug in, okay, blindly the gauge field propagator? So what happens? Okay, this is the expression of the gauge field propagator for a linear covariant gauge in principle. Okay. Wait. Okay, it's already here. The topological invariant is trivially 0 for any topological invariant. Doesn't matter the K. Doesn't matter which matrices we put here. This will always be 0, exactly because of this structure here, which is anti-commuting, okay? And the gauge field propagator is bosonic, so it is trivially 0, always 0. So what to do? So our proposal is that there is a one-to-one correspondence between the gauge field propagator with these two structures here, okay? And this structure is a very specific one. It has this form, this shape here, okay, which is a p slash. It can be plus or minus, okay, and a dynamical mass. Okay, this is general. This is not only for Gribov propagator. This is general for a dynamical mass. If you multiply delta plus and delta minus, you recover the gauge field propagator. And I would propose, this has no, in principle, we don't know, in principle, it has no physical meaning. This is just
A parametrization.
a parametrization, exactly. And now we propose to look at another topological invariant, which is not written in terms of the green two-point function, but written in terms of this new structure, which is not a green two-point function, okay? The green two-point function is the product of the two terms. So let's compute what's here, okay? Mathematically, they satisfy, it's a one form, okay? So it is exactly the same. This is a topological invariant if the condition are satisfied. Commutation, okay, of the symmetry, and boundary condition, the same. And the boundary condition can be read out of this expression here. So pay attention. Here we have more or less the Fermat propagator, the Fermat two-point function. So what we have to do now is just to mimic and see what happens for the gauge field. We are considering, since it's massive, since it has a dynamical mass, we must consider the gamma 0, gamma 5 structure the same, and we arrive at this expression here, where m prime is the derivative with respect to the momenta, okay? For the specific case of the lattice gauge field propagate, the lattice, it can be any, but according to this paper here, the lattice gauge field propagate can be fitted by something of this form, okay, this shape. For instance, the refined Gribov propagator satisfied this condition, and the Gribov that I showed you is satisfied when S is 0 and U is 0. S and U is 0, you recover the Gribov propagator, okay? But I made sure to not write lambda without the Gribov propagator, because this is just lattice. This is what lattice tells us about the propagator. So the dynamical mass can be computed like this, just following this condition here, okay? We can get the expression, and just the derivative is like this. Let's compute the integral, the topological invariant, and what we find is that the topological invariant, sorry, one mistake, it shouldn't be written lambda, exactly because the topological invariant is gauge independent, as should be, okay? It's a number, and it does not depend on the gauge, so there's no meaning to write lambda here, okay? So the topological invariant is equal to 1. This is not 0 as before. Remember that for the gauge field propagator, the topological invariant is always 0, but for this new structure, which is not a green function, this is 1 for any value of the parameters, except for t equals 0. T cannot be 0.
T, can you go back? T, what is T?
T is exactly the Gribov parameter.
Okay.
Okay? So t cannot be 0. If t is 0, the integral cannot be solved. Just like this. which is exactly what happens for fermions. When we consider massless fermions, we could not use the same topological invariant, we have to use another topological invariant. Okay? Since we are using this massive kind of fermions, okay, we cannot put t equals 0, which would mean the massless case. Okay? So, this is one. Well, the boundary condition is satisfied, so this is true, a truly topological invariant. The number is not 0, as we were getting for the gauge propagator. There is no topological difference between GZ and RGZ, as I mentioned before. RGZ is just like this. The refined Gribov procedure is just like this. For Gribov, just put S and U equal to 0. So they are topologically equivalent, Gribov and refined Gribov. In the case of massless gauge in the ultraviolet, let's see what happens when we recover the ultraviolet limit. It is equivalent to the Karl fermion situation computed by Volovic, and we should compute this with other topological invariants, so we cannot compare. Okay, it's not comparable because we compute with different topological invariants. So this is our proposal, and we believe that if we have, for instance, our next step is to see. I've already computed, but if we compute, for instance, SU2 with Higgs, okay, Higgs will require a mass to the gauge field, more or less to say, okay, and consider Gribov. So we have two massive parameters to play with, which is the Higgs mass, okay, and the Gribov parameter, and then we can see if we can compute a different number than 1, and indeed I'm finding 2, but I just not put it here because it's still really new in the sense that I computed this quite recently. So you see, this is the proposal, to try to see topological phase transition with the gauge field propagator, proposing a structure that can reconstruct the gauge field propagator. And I don't know about the time, if maybe too early, if it is, I don't know. And thanks, this is
If anyone has questions.
Sorry, I didn't get the last part because in other cases I understand the meaning of the topology, which is characterized by the topological invariant. But here, for example, you speak about topological transition, but your number doesn't, in fact.
No, exactly, because I'm not comparing with anything. In principle, in the first beginning, we were thinking, let's compare the massless, the ultraviolet, with the infrared Gribov, blah blah blah. Okay. And then we just realized that we cannot, because the massless can only be treated with a different topological invariant of the massive. Okay, so we cannot say anything between them. So what can we do? We can take only the massive and try to play with the parameters of the mass and see if the number changes. Okay.
Okay.
And then what I'm telling is that if I work in pure Young-Mills SU2 plus Higgs, it can be done because we have two independent massive parameters. Okay, and I really believe that we find different numbers. So what we have the same topological invariant with the same symmetry. Okay, the symmetry is not broken or anything. The system is exactly the same, but the topological charge changes from 1 to 2, perhaps. Okay, we have to check, we have to see. And then we would see a topological phase transition.
Okay.
You see? Okay, but the fermionic standard computation, they have a more, they can compare with topological materials. So they have all the interpretations, blah, blah, blah. Here we are just interested about different topological numbers, charts.
Okay.
So do the topological invariants characterize a phase of the, I don't know,
Yes. Yeah, they characterize a state of the system, depending on the chart.
A different number of these topological invariants could indicate the change of a phase?
Yes, a topological phase or a topological class. You change you have universality class.
So you could not necessarily need to compare the derivative, I mean to use the two-point function, but you could use other endpoint functions and trace it through with all the indices, right?
Well, yeah. At this point, you're reaching the region of my ignorance, okay? Because the
because the phase is indicated by the behavior at some level. So the endpoint function could also tell you other things. The phase transitions could be in other structures of the theory, right?
Yeah, indeed. Let's look at it here. Forget about gamma 5, gamma 0. Okay, let's look just to the structure. Okay, the structure depends on G and dg minus 1, and this. And here we depend on the fact that G is dg is a one-point function. So I don't know if any point function still is a one form. We depend on the fact that dg, the Gribov parameter, is a one form, okay, in topology. So I don't know what happens if any point function is still a one form. Do you know about this? So I don't know if I believe that it's possible to construct a topological invariant with any point function, but I really believe that it will be completely different.
Yeah, I was thinking about this because I don't like the fact that you use the delta construction afterwards.
Yeah.
What does it mean to use delta over there? I don't find any meaning.
Yeah, physical meaning there is not. Physical meaning there is not. We are just. The question is it possible to find something hidden if we rewrite? We are just rewriting the two-point function in this way, okay? And the question is, can we get some new information if we rewrite in this way? Okay, we could do the computation and realize that no, we cannot. This is just the same. But you see, so it opens many doors to rewrite the Gribov two-point function in many ways to see if new information pops up. You see, but this is just.
Igor, one last question. But this is just purely bibliographic question. The work you presented on finite temperature is the one you have done with Pablo Pais and these people. It's that paper. I remember that paper.
I believe you know very well which paper is this one.
Yeah. But you never have done this as similar stuff up to the end with refined Gribov.
No, because refined Gribov, as you really know, refined Gribov once again is not really a first principle. It's just fitting more or less, because you know what I mean.
Know how to
so you don't have the gap equations.
Yeah. Okay.
You don't have the gap equations. So how to solve the finite temperature?
Okay, I understand.
Thank you very much.
Thank you so much. Yeah.